Bradley, he worked from England from an observatory. He didn't have his own laboratory at the time. The equipment he used mainly was a telescope called a zenith sector, which is a telescope that can only be moved up and down. For him to use it, he waited for the specific stars to pass by the telescope to measure their exact position over time. Because of this, he recorded a bunch of data, hundreds of data by hand. Some of the difficulty was he had very limitations with the telescope. It had to be perfectly still. The temperature changes and the vibration, all that made it harder for him to capture what was needed. He had no tools that could directly measure how long it took light to reach Earth, so his results was indirect, and that led the scientists to be skeptical about his own theories. His original motivation was he wanted to detect the parallax of the stars, but he seen the shift in the stars is not what he expected. He figured out that it was stellar aberration caused by finite speed of light. This accidentally revealed that light doesn't travel instantly. His discovery of stellar aberration gave observational proof that Earth moves around the sun. He independently confirmed that light travels at infinite speed and not instantaneous. Because of this, the star map and celestial charts were much more precise and made navigation way easier. Unlike Bradley, now labs are controlled in a laboratory setting, such as research centers. They have as equipment such as lasers, as light beams, beam splitters to compare, and photo detectors to measure the exact arrival times and much more. Modern measurement uses speed of light to Modern measurement of the speed of light use controlled laboratory lasers and precise digital sensors, unlike historical experiments that relied on mirrors, rotating wheels, and observations. They have more stricter safer protocols now, including laser protection goggles, restricted access to high power of laser areas, and careful handling of optical and electronic equipment to prevent damage. Some modern benefits is they can know the exact speed of light now, and it allows for more accurate measurements in physics, engineering, and astronomy. Education and research training benefits because student scientists learn precise measurements, optics, and data analysis, which is the foundation of many STEM fields. Things like GPS, laser technology, and satellite navigation became about because of this study. Some future expectation is that it led to more scientific and technological benefits such as telecommunicators, GPSs, space navigations, and many more. They also in the future want to have more advancement in quantum communication, optical commuting, space exploration, and high precision measurement standards, as well as potential discoveries and more medical technologies.
Hi everyone, it's Maida. This is the speed of light part C, and we're starting off with the original process. The original process, O. Romer, a Danish astronomer, was the first to measure the finite speed of light in 1676 by observing Lo's eclipses through a telescope. He noticed timing differences depending on Earth's distance from Jupiter. From these delays, he proved that light travels at finite speed, not instantaneously. Original difficulties. Early telescopes had poor lens quality often um, and weather often blurred Lo's eclipses. Accurate timing tools didn't exist, so Romer relied on mechanical clocks and rough estimates. Many scientists doubted his results, assuming errors rather than true light speed delay. Original motivation. The original motivation, Romer wanted to explain why Lo's eclipses didn't match predictions and to test whether light's speed was infinite or limited. Inspired by Galileo's earlier experiments, he used celestial rather than ter- ter- sorry, terrestrial measurements to seek a universal truth about light. Original benefits. His findings confirmed light travels at a finite speed, influencing later studies by Bradley and Michelson. This shifted science from philosophical ideas to quantitative astronomy and changed our understanding of time and space. Um, Modern processes. Today, scientists use lasers and atomic clocks to measure light speed with extreme precision. A laser beam travels through a vacuum and reflects back, and its travel time is timed electronically. NASA also uses this technique to measure distances to satellites and to the moon. Modern differences. Unlike early astronomers who relied on observation, modern scientists use digital instruments and vacuum systems. Data is recorded automatically, removing human error. Fiber optics and laser systems now measure light with accuracy down to nanoseconds. So, modern benefits. Modern benefits, knowing light's exact speed allows synchronization of GPS satellites, internet communication, and medical lasers. It supports Einstein's theory of relativity and helps scientists calculate astronomical distances with incredible accuracy. And last, the future expectations. So, future research aims to test a light speed is always constant in every environment. So, quantum communication and laser teleportation could, I'm sorry, could revolutionize data transfer between Earth and Mars. Quantum physics may also redefine how we measure time and space.
My name is Griselda Romero, and my topic is speed of light. For original process, I did Galileo's lantern experiment. The experiment took place outdoors on distant hilltops at night. Galileo and his assistant used two covered lanterns and stood a few kilometers apart to ensure clear sight. He used two handheld lanterns covered by shutters and counted to measure. Galileo uncovered his lantern to send a light signal. When the assistant saw the light, he would uncover his own lantern to send the light back. Galileo measured the time delay between uncovering his lantern and seeing the light. He tried at different distances to check for a measurable delay. Galileo had no accurate timing tools, as stopwatches didn't exist yet. The distance between hills were too short for human reaction time to detect delay. Some issues were looking in the dark, uneven hills that increased risks of falls or injuries, carrying open flame lanterns posed as a fire hazard, as well as long distance between them made communication difficult and potentially unsafe. Lanterns with shutters were not precise, and the distance between observers was hard to measure accurately without modern technology. Human reaction time was far too slow to detect light speed. Galileo's main goal was to test whether light travels instant or takes time to move. He wanted to measure the speed of light directly using observable methods with two lanterns and human timing. The discovery was intentional. However, the results, light appeared to travel instantly, revealed the limits of his tools, not the true speed of light. Astronomers got a better understanding of how light travels. Galileo's attempt inspired later scientists to create more precise methods for measuring the speed of light. Even though Galileo couldn't measure the exact speed of light, his experiments proved that testing light's motion scientifically was possible. He introduced the idea that light might not be instant, which inspired more precise research in later centuries. Galileo's attempt laid the basics for quantitative experiments on light, showing that light could be studied like any other physical phenomenon. In mathematics, scientists began designing formulas and timing calculations to measure fast speed of motion. Galileo's experiment helped guide towards modern physics, influencing discoveries like Roemer in 1676 observation. Conducted in controlled physics laboratories, experiments are often performed in vacuum chambers to eliminate interference from air. Lasers provide a stable and straight line. Mirrors and beam splitters are used to reflect and divide light beams for timing comparison. Laser beams are pointed towards a mirror placed at a known distance. The beam then reflects back to detector and measured electronically. Modern experiments use lasers, mirrors, and digital sensors instead of lanterns and human eyes. Light speed is now measured with extreme precision using interferometers and atomic clocks. Scientists work in controlled laboratories environment with safety goggles to protect against laser exposure. Data is collected through digital sensors and computer interface instead of human observation. Results are processed using computer algorithms that calculate light speed instantly. Modern light speed research helps improve precision in navigation and communication. In medicine, imaging technologies such as MRI and laser surgery depend on precise light measurement and behavior. Fiber optic cables that help transmit data near light speed for global communication. Scientists aim to improve precision in measuring light under extreme conditions. Physicists also continue searching for ways to use light for faster communication. Potential benefits is faster global communication through quantum or photonic internet technology. More accurate space exploration by using light-based navigation system.
Hello, my name is Hector Saavedra, and I'm going to be talking about the speed of light, group project part C. Original process. In the mid 1800s, these experiments were done in large open spaces with long optical paths. One major equipment was a strong source of light for the day, often an intense lamp, an arc lamp, or otherwise bright source, which could send a narrow beam across the optical path. The light beam was sent through a spinning toothed wheel or reflected off a rotating mirror, then traveled to a distant mirror and bounced back. By carefully adjusting the speed of rotation, they looked for the moment when the returning light became blocked or shifted out of alignment. Original difficulties. Early optical experiments were done often done outdoors over long distances or inside dim mechanical workshops. Bright arc lamps and open flame light sources could cause burns or fires. Rotating machinery such as high-speed toothed wheels pose serious physical hazard if misaligned. Gears, bearings, and support beams weren't perfectly engineered and introduced vibration and misalignment. Any misread timing or angle could cause large calculation mistakes. Original motivation. Physio aimed to measure the speed of light on Earth in a terrestrial experiment rather than relying on astronomical observations. Physio intended to measure the speed of light using his cogwheel apparatus and distant mirror. He planned the apparatus, selected the wheel, chose the long pass, and deliberately increased the wheel speed until he observed blocking of the returning beam. His work was aimed at enriching the scientific foundation of optics and motion of light. Original benefits. It laid groundwork for the later development of the theory of special relativity by showing that assumptions about light's propagation needed rethinking. With light speeds being measurable, the concept of time and distance measurement tightened. It helped standardize distance and time relationships in science. The realization that light is not instantaneous forced a conceptual evolution. This seeded fields like Einstein's physics and modern cosmology. Modern process. In a modern physics laboratory, the environment is highly controlled and equipped with advanced technology to ensure precision in light speed experiments. The room is usually darkened to help detect faint light signals accurately. The typical procedure begins by sending a laser pulse through a measured path, detecting the returning signals with a photodiode, and using electronic timing devices to calculate the light's travel time. Multiple trials are performed, and computer software help analyze and reduce errors, making modern measurements far more accurate and reliable than early experiments by scientists like Armand Fijot or Albert Michelson. Modern differences. Modern advancements in measuring the speed of light have made experiments far more precise and efficient through the use of lasers, high-speed electronics, and computer-based analysis. Modern protections and safety measures include laser safety goggles and automatic shut-off systems to prevent eye or skin exposure. Information gathering is now done using digital sensors, photodetectors, and oscilloscopes that record light travel times with nanosecond or even picosecond accuracy. Information processing is performed with powerful computer software that automatically calculates, graphs, and compares results to theoretical values. Modern benefits. Studying light's behavior with extreme precision, scientists have improved our knowledge of relativity, optics, and electromagnetic theory. It benefits many fields including astronomy, communication, and medicine. Precise knowledge of light speed helps measure cosmic distances, improve fiber optic internet, and develop medical imaging tools. Medical imaging technologies like laser surgery and optical coherence tomography rely on principles learned from light speed studies. These advancements have led to technologies such as GPS navigation, laser rangefinders, high-speed internet, and advanced optical sensors. Future expectations. Future goals for scientists studying the speed of light include finding even more precise ways to measure and control light, exploring how light behaves in extreme conditions, and using it for faster communication and computing. Researchers aim to develop technologies such as quantum communication systems and photonic computers that use light instead of electricity. The potential benefits include faster and more secure data transfer, improved medical imaging, and breakthroughs in understanding the universe.